So in this video, what I want to do is to look at the Maclaurin expansion and the binomial theorem. And here is the binomial theorem written out. So if we have 1 plus x to the power of n, and I'm thinking of n as a natural number, a positive integer, 1, 2, 3, 4, etc., then we can write this according to the binomial theorem as the sum from j is 0 to j is n of x to the j multiplied by an integer coefficient of choose j from n, whose exact definition I hope you know, but if not, it is n factorial divided by j factorial and also divided by n minus j factorial. Okay, so that's the binomial theorem. This is a polynomial. You expand this, it's going to be a polynomial. The highest term is x to the n. It's a polynomial of degree n. This is the Maclaurin formula. And for a polynomial of degree n, we're going to stop here. So it's the function evaluated at 0 plus x times the first derivative of the function evaluated at 0 plus x squared over 2 factorial times the second derivative of the function evaluated at 0, etc. And what I would like to do on the next slide is to show that this, for this function, generates this. And I'd suggest that you try it first with pen and paper, and then in a moment I will give you the detailed explanation of it. So see you in a few minutes. Okay, welcome back. Let's look at how to obtain this from this. To calculate a Maclaurin expansion, I think the right thing to do is to write out the formula. So for a Maclaurin polynomial of degree n, this is the formula. Here is our function, 1 plus x to the power of n. So what is the Maclaurin polynomial? Well, this is our function, and if we evaluate it at 0, we just put x is 0 in here, we get 1 to the n, and that is 1. We then work out the first derivative by differentiating this. So you're going to bring an n in front, reduce the power by 1, you go to n minus 1, and then from the chain rule you multiply by the derivative of the argument of the brackets, but that's just going to be a 1, and we don't need to write down times 1. So the first derivative, evaluated at 0, we just put x as 0 here, and we have n times 1 to the n minus 1, and that is just n. The second derivative is obtained by differentiating this, and you can see the structure of writing it this way is useful. We just have here something which we're differentiating. We bring an n minus 1 in front as well, and then we reduce the power by 1 plus x to the n minus 2, and then we multiply by the derivative of 1 plus x, but that's just 1, so we don't need to write it. So we obtain n times n minus 1 times this, and when x is 0, that's just n times n minus 1. And then we carry on to the next term, we bring an n minus 2 in front, n times n minus 1 times n minus 2, times 1 plus x to the n minus 3, reducing that power by 1, and multiplying by that derivative, which just gives us a 1 that I'm not going to write. So the third derivative, but now evaluated at x is 0, is n times n minus 1 times n minus 2, multiplied by 1, n minus 3 times, and we don't need to write those down. So it's just this. And if you carry on doing this, then I hope you can see that the nth derivative, you're going to generate n times n minus 1 times n minus 2 times n minus 3, all the way down to 1, and that's going to be n factorial, multiplied by 1 plus x to the n minus n. In other words, multiplied by 1 plus x to the 0. And something to the 0 is 1, so the nth derivative of the function for any x is just n factorial, and the higher derivatives are all going to vanish. So what we see is that the expansion of 1 plus x to the n is 1 from the first term, plus n times x, so that's this, x times the first derivative evaluated at naught. I'm just writing them the other way in the other order. So it's n times x, and then we have x squared over 2 factorial times the second derivative at naught, and that's n times n minus 1. I'm just putting the constants in front of the x squared. The x cubed term is this, and it carries on. And then we've already said that the x to the n term divided by n factorial from the formula is going to be multiplied by this, which we have said is n factorial. So this is what we would get. If you wish, you could just repeat this with, say, n is 4 and just work out the terms explicitly. Now, this is the binomial expansion, but it doesn't look terribly beautiful, does it? So let's try to rewrite this in a way where we see the structure. So what we have is, let's look at this term, n times n minus 1. That's part of a factorial. N times n minus 1 times n minus 2, that's again part of a factorial. So what we can do is we could say, well, this is n factorial, but n factorial is n times n minus 1 times n minus 2 times n minus 3, etc. So if we want to multiply by those terms on the top, we have to multiply them on the bottom as well. So this would give us n factorial over 2 factorial times n minus 2 factorial. Those are the extra terms. So what we're obtaining is that 1 plus x to the n is going to be equal to, and I'll leave the 1 for a moment, the nx is going to be plus n factorial over, and now n is related to n factorial in that n factorial is n times n minus 1 factorial. So I have to put here on the bottom an n minus 1 factorial, and that partly cancel, and it would leave you with n. So that is going to give us that. And I'm just going to put here a 1 factorial, which is, of course, 1 by definition. And that's going to be multiplied by x. The next term is n factorial again. And now we have a 2 factorial from this expansion. And then we also, to rewrite this as n factorial, we have to divide by n minus 2 factorial. So again, if you expand this, this is n times n minus 1 times n minus 2. Oh, and that would cancel with a bit of that. Times n minus 3 would cancel with a bit of that. So this ratio here is n times n minus 1. And that is this constant, and it is multiplied by x squared. And in the similar way, the next term is n factorial over the 3 factorial, which comes from the formula here, times n minus 3 factorial. And again, you can convince yourself that this divided by that is n times n minus 1 times n minus 2, and that's going to be multiplied by x cubed plus n factorial at the end. And on the bottom, well, you notice that here we're going from 1 factorial, 2 factorial, 3 factorial. So I'm going to write this n factorial here at the very beginning. And this is going to be multiplied by 1, but I can always write 1 as 0 factorial, and this is times x to the n. So you may be wondering why I've not written 1 factorial. If you look at the term before, what you will see is that you'll have n factorial over n minus 1 factorial times 1 factorial. In the same way, it's 3 factorial, n minus 3 factorial. So this is n minus 0 factorial times 0 factorial. And if we go back to the 1 at the beginning, the 1 is x to the 0 times n factorial divided by 0 factorial and an n factorial, so that this is indeed 1. The n factorials cancel, 0 factorial is 1, x to the 0 is 1. And this we recognize as the binomial expansion of 1 plus x all to the power of n, because we remember the definition of the binomial coefficients, and the binomial coefficients choose j from n are n factorial divided by j factorial and also divided by n minus j factorial. So in this way, what we have obtained is from the Maclaurin expansion of 1 plus x to the n, we have obtained the binomial expansion. So we see here that we have x to the 0 multiplied by the binomial coefficient n factorial, 0 factorial, n minus 0 factorial, so this is choose 0 from n, plus x to the 1, and then this is the binomial coefficient, choose 1 from n, and this is just our expansion. And we could write that as was written on the very first slide in terms of a summation from j is 0 to j is n. So it is a summation with n plus 1 terms. And what I've really been trying to do in this video is just to show to you that the coefficients in a Maclaurin expansion or a Taylor expansion have a meaning. They tell you an awful lot about the function. And for this function, which is itself a polynomial, the Maclaurin expansion gives you the entire expansion of that polynomial. So it agrees entirely with the binomial theorem. And on the next slide, I'm just going to give you some exercises to practice manipulating factorials. So what I would like you to do is to rewrite this purely in terms of factorials and to rewrite this purely in terms of factorials. And then, and this is rather harder, I would like you to show that the sum of these two binomial coefficients gives this binomial coefficient. And that is something which may very well be familiar to you from Pascal's triangle. So you have various numbers in Pascal's triangle. I'm not going to bother writing them out. And you know from Pascal's triangle that if you have one particular row, then to obtain the next row, what you do is add 2 from the row above. So say this and this together, and their sum gives this coefficient. And that's exactly what's happening here. So you increase the number of the row to the next row, and you go from k and k plus 1 to k plus 1. And showing this is just a matter of manipulating the factorials. With that, I will essentially stop the video, but on the next slide I will show you the answers. So please have a go at them before you look at the answers. Okay, welcome back. The answers are about to appear. And here are all 3 exercises, and as said, this is the one that requires the greatest amount of work. With that, I will stop this video.